Bueno, de nuevo, creo que eso fue todo. Hola a todos, muchas gracias por venir, muchas gracias a la gente que está en Zoom conectada en sus casas. Hoy, en esta sesión pre-18, pre-fiestas patrias, tenemos el agrado de contar con Gabriel Marin, estudiante de Magíster en la Universidad de Chile, y hoy nos va a hablar sobre su trabajo titulado Celestial Strings. Así que un aplauso, por favor.
Great. So thank you. Thank you for the very kind introduction. So this is going to be talking English, so I'm sorry if you are bothered with that. So anyways, as you're already heard, so I'm going to tell you the story, which is titled Celestial Strings. So this was a work that we uploaded to the archive. You can check it out using the number video. And this one's done in collaboration with Lina Castillo. She's a postdoc at Newcastle University in the UK. He's a professor at New York University in the US, and Francisco Rojas, he's a professor at Adolfo Ibáñez University here in Chile. All right, so great. Okay, so here's the outline of my talk. So it's going to be basically two halves. So the first one is going to be me telling you about this motivation and basics about this new research that's going on, which is called the Celestial Holography Program. I'm also going to introduce whether we care about string theory in this context. And yeah, on the other half, it's going to be me telling you about this celestial string setup in order to do some computations. So we're going to be interested in the case of amplitudes. How do we talk about amplitudes in this context? And yeah, I'm also going to be discussing the string theory version. So we're going to be roughly nothing to a deep level about the string amplitudes. And then I'm going to be discussing one of the topics that we cover in the paper, which is the field theory limit. All right. So yeah, okay. Let me start with the motivation. So let me state that quantum gravity is still one of the biggest puzzles in modern theoretical physics. Where, but just saying quantum gravity, I'm just referring to any theory that behaves like Einstein's general relativity at long distances. So in this context, there has been significant progress in the rotational bulk scattering of asymptotic, ADS space, which is, of course, we all know that it's just the space with negative cosmological constants, where one can make a holographic identification to a lower dimensional field theory, which is actually a conformal field theory, so just CFT for short, living on the boundary. Okay, so this, of course, is a very known relation that people refer to them as the ADS-CFC correspondence. It was first introduced by Juan Maldacena in the late 90s. Okay, so now we could then wonder, do we have anything similar in the case of flat space? Can we say that we have something as a flat space holography? Okay, this is a question that we want to answer. So, okay, but first, if we want to study more about this question, we first have to frame it into more a physics perspective. So now in physics, of course, we're interested in observables. So if we're going to be discussing a quantum group theory, one of the primarily observables are scattering amplitudes. So here I have a scattering process described by this double Penrose diagrammatics. So if you're not quite familiar with the Penrose diagrammatics, let me quickly review it right here. So here's the double Penrose diagram. So the blue line corresponds to the world line of massive particles, while this wavy red line corresponds to the world line of massless ones. So the massive particles, they enter and exit this diagram at these 2 points over here. So little I minus and little I plus, corresponding to past and future time like infinity. So in the case of the massless particles, they enter and exit this diagram at these these lines over here. So big I minus and big I plus. And we verbally refer to those lines as scribe minus and scribe plus, and they correspond to past and future null infinities. Okay, yeah, so we can then observe that we can parameterize these two lines with these parameters over here. So B corresponding to the advanced time, describing scribe minus, and U, which is the advanced time, sorry, the return time, describing scribe plus. You can then go on and study what's going on at the topological level of these lines over here, and you're going to see that it's composed basically of real lines and an S2, which is a sphere, which is the one that we refer to as the celestial sphere. Okay. Also, another very interesting point in this Penrose diagram is the I0, as I have it right here. So it corresponds to the space infinity, basically. So this is a really interesting point because you can obtain a really nice set of antipodal matching conditions on the sphere, so on this S2, And yeah, you obtain that basically understanding what's going on the physics at this point. So yeah, just a really nice shout out to this book. Okay, so now I can roughly tell you what celestial holography actually means. So it refers to a duality between gravitational wave scattering of asymptotically flat spaces and the conformal field theory living on this solar sphere. In other words, we say that a four-dimensional quantum gravity equals to a two-dimensional celestial conformal field theory. Okay, so we don't fully comprehend this dual description, at least that. We know it has some properties of a 2D CFT. However, there are some subtleties. I'm definitely at least going to mention one in this talk. So yeah, this is the reason on why we just don't write 2D just a 2D vanilla CFT. Instead, we add this extra C, referring to the celestial behavior. Okay. So now, let me answer to the natural question that could arise, which is why do we actually believe in this duality? So now, in this talk, I can tell you roughly about 2 hints. So the first one comes from the study of symmetries. So you can see that the Lorentz group in little d plus 2 dimensions acts on the sphere as the Euclidean conformal group in little d dimensions. So if you want to put some numbers, the Lorentz group in 4 dimensions is acts on the sphere as the Euclidean conformal group in 2 dimensions. If you want to see the exact same statement from a group theory point of view, you can see that the proper orthogonal Lorentz group, so SO plus 1,3, is actually isomorphic to SO2C quotientated by the center, which is Z2. Okay, so there's a very nice set of matching at the level of symmetries. So yeah, this is the first hint.
I have a question. I don't know if that's really a hint, because in quantum physics, when we talk about celestial, conformal field theory, and then they use the embedding formalism, they matches the kinematic like that, and nobody in that context talking about duality.
Yeah, that's the story. We could just say that it's a hint 0 in some sense, because okay, this is just a matching of the level of symmetries. We agree with you with that. This is not entirely a hint. Maybe we just could say just a half a hint. So there's some matching on the symmetries. But yeah, you're correct. Okay. So now with the proper first hint, or as I have it here, the second one comes from the study of observables, particularly the S matrix. So from a long time ago, we know that if we want to describe some, let's say, some massless asymptotic states, we can describe it by choosing some energies and some points in the sphere, as I have it over there. When we do that, we say that we are parameterizing the S matrix and describing it using the energy momentum basis. So here's the picture of it. So we have the initial data leaving at square minus. We have this scattering process actually happening in the bulk. And we have some final data at the square plus. Of course, this is only valid for massless particles. Okay. However, if we want to study what's going on in the celestial sphere more effectively, we instead use these spaces over here, corresponding to some delta and some positions on the sphere, where this delta is basically the boost eigenstates on the sphere. When we do that, we say that we're using the boost rate basis. Yeah, you can go on and convince yourself that this delta is actually the conformal dimension of a 2D CFT. So yeah, so just that. Okay. So also, so now these 2 bases, they're not disconnected from each other. So there you can actually go from one to another by performing this Marin transform. So it's essentially an integration over all energies. So an integral over 0 to infinity of the omega weighted by this delta. So in some sense, we're doing something in the same spirit of what we do in a typical quantum field theory course. So if you recall, in quantum field theory, we typically start studying things in position basis, right? And then we move on to momentum basis because just things are easier. So yeah, here we're doing something on some line. We're starting from the momentum basis and we're moving into the boost point basis, or if you just want to call it, we could say the social basis by taking this transform. So now here's a small comparison of the 2 objects of interest. So on the energy momentum basis, of course, we're interested in computing stellar amplitude, which are given by the S matrix in this following form that we have over there. And now in this celestial basis, we're interested in computing celestial amplitudes, which are given by a correlation function of some operators that depend on the position on the sphere, so D of the mark, and these deltas. And yeah, these minus and pluses over here are just telling you the information of if the particle was incoming or outgoing. Okay, so yeah, something really interesting about these correlation functions is that they have definite transformation properties onto the global conformal group. So yeah, some very nice property about these selection objects. Okay, yeah. So now, of course, in the standard amplitude sector, we know that we have some manifest translation symmetry. So in this selection sector, we instead have manifest Lorentz symmetry. That if you recall the symmetries slide, we said that the Lorentz group is equal to the global conformal group in 2 dimensions. So yeah, here instead we have manifest Lorentz symmetry, which is equivalent of saying that we have manifest global conformal symmetry on the sphere. All right. So
sorry, what is corresponds to translation symmetry on the other side?
Sorry, in this side, in the selection side, we have Lorentz symmetry, manifest Lorentz symmetry. I can show you the calculation later. Yeah, it's a really fun calculation that you can do on these calculations. Okay. So there's a little caveat that I do have to tell you about these correlators. So that's okay. They behave quite nicely. However, there's a certain appearance of some kinematic deltas coming from the energy momentum conservation from standard amplitudes, especially when you're computing lower parameters. For instance, when you starting for look at the 3-point level, so 3-point correlation function. So okay, there's this distribution of behavior. So why is this a problem? Even to start. So yeah, you can recall your 2D CFT knowledge. You can probably remember that the 3-point function in the 2D CFT is very much constrained, right? Because of conformal symmetry. So you can constrain it up to a constant, right? So this constant should be distributed. That's what this is telling us. Okay, so this is weird. And there's also the fact that you can use property called the operator product expansion, or just OPE for short. So the OPE essentially allows you to write down endpoint correlation function in terms of n-1 point points. So yeah, this distributional behavior gets propagated into high point correlation functions. So okay, this could be a problem if you just insist of having a 2D CFT, 2D vanilla CFT. However, if you embrace that, okay, this is not a 2D CFT, and we have this extra C and say that this is a large CFT, this is not a problem at all. You can solve this by using, for instance, leaf amplitudes. But yeah, this is still a discussion topic in the community. Okay. So now let me draw a real nice picture so we can have a better understanding of the topic. So from a long time ago, we have been using this omega, right? So the energy momentum basis here represented by this omega. I've also described this new basis. So this celestial basis or Kurzweil basis, and of course it's related by this Marin transform. However, you can still insist of studying the conformal boundary by using the position basis. So here is depicted by the U, which is the parameter that we use to describe spheric plus. Of course, position and momentum space, they're related up to a Fourier transform. They have it over here. But it's also a possibility of going from the position basis to the celestial basis. So in the more of a recent work, yeah, you use this transform here, which is called the Large transform, which is essentially an integration over all these U variable and weighted by this. So it was done by these authors over here. Okay, so now there's a reason on why do we actually care on these of these three bases that they're kind of like forming a triangle. Okay, and that's when studying lower energy physics, or just we can say IR physics. Seems to be quite nice to use different corners of this triangle here. Yeah, this concept is so referred to as the IR triangle. So in the momentum basis, of course, is quite nice to see this up here. So it's a really nice factorization. I'm going to be explaining just in a second what's going on in the case of gravity, so we can have a better understanding. But okay, in the position basis, of course, we have the memory effect. And in this new basis, over here, this larger basis, due to this manifest Lorentz symmetry, it seems to be quite nice to study the asymptotic symmetry behavior. Okay, so let's get an example so we can have we can understand this more. So okay, so here's the leading gravity IR triangle. Okay, on the bottom right corner, we have the gravitational memory effect. So this was first studied by Sedlovich and Polnareff in the 70s. Okay, so it refers to a memory-like displacement of to the detectors due to the single gravitational wave. So here I have a small animation so we can understand it more. So okay, imagine that we have a circular detector with initial diameter g naught. Okay, so here's the gravitational wave passing through the detector, so it has an oscillatory behavior on the circle. And here's the final outcome. You can then measure the final diameter, and you're going to see that's different from the original one. So in some sense, we say that it remembers the gravitational wave. Okay, so this is a theoretical prediction. I think it's 1974. But yeah, that's still hope to measure it experimentally by this ELISA in this spatial interferometer. So yeah, hopefully we can say more about the experimental side of this triangle later on.
Sorry, so gravitational waves make things longer or something?
Sorry?
Gravitational waves makes things longer?
Makes not necessarily longer. Well, it depends on the parameters of the wave. But yeah, you can see a distortion. It's really small actually. But yeah, you're supposed to see.
I think it's the relative distance between objects that gets longer.
That makes more sense. Yeah.
You're asking. Okay, I misunderstood you. Okay. So yeah, that's the gravitational memory structure. On the bottom left corner, we have the soft Gabriel term, which was first studied by Stephen Weinberg in the 60s. Okay. So it refers to a really nice structurization going on. So let's suppose that we have this scattering process, and let's also suppose that we attach an external graviton on one of the external legs. So the theorem states that if you take the energy of this external graviton to be really small, or to be near zero, you're going to see a very nice factorization going on involving a universal factor where you can extract really nice physics from this factor over here. So in the case of gravity, you can impose the symmetry, and yeah, this factor over here is it's going to give you the equivalence principle multiplied by the original amplitude stripped from this subgravity. Okay, and on the top corner we have the BMS symmetry. So in the 60s, Bundy, Vandenberg, Metzner, and Sachs, they tried to answer to the question of what is the asymptotic symmetry group of asymptotically flat spaces at null infinity. Well, they discovered that it was not incorrect, which was the naive expectation, because they were dealing with asymptotically flat spaces. So instead, they found an infinitely enhancement of Poincare, which we now call the BMS group. So it has these added symmetries over here, which are called super translations. So essentially, they're translations that depend on the direction of the null infinity. So here I have a picture of it. So let's say that we apply a super translation on this time u. So we say that the retarded time u is shifting independently at every angle inscribed. So we can see it visually here. So these arrows have different lengths that are dependent on this function over there. So yeah, that's in a nutshell super translation. All right, so okay, so this is the case of this full leading gravity IR triangle. So now, of course, this is not strictly applied to gravity. We also have many more versions of this triangle over here. So we also have the theory triangles. So we have a QED and Young-Mills versions. And yeah, more recently, we know more about the subleading version of the gravity IR triangle. And yeah, there's also the proposal that this could be applied to different areas of physics. So for instance, we could have a cosmological IR triangle, maybe in the future. Yeah, there is many more incomplete versions of this triangle here.
Yeah. And you talk about this transformation between different bases, and then you relate that to this triangle of different like properties of gravity. There's the BMS, the theorems, and the numerical. How are they connected? Because from the main transform, I don't see like the Guardian identity from the sub-theorem.
Wait, here, right?
Yeah.
I mean, this is not a, you can study BMS, for instance, without talking anything about what's going on in the celestial sector. That is true. That is true. Instead, well, indeed, it was originally done. I think this relationship was in 2014, I think, or 2013, before celestial holography. So yeah, so this is just a schematic example. You can still understand this without talking anything about celestial. Yeah. You can also do it talking about celestial. Yeah, actually, the sublattice version, it was done on the, you can understand the top sector, so the symmetry sector on the celestial basis. I don't think it's well known in the non-celestial. I don't think so. Oh yeah. Great. Okay. So, okay, now let me introduce the string part of the story. So why do we care about string theory? Right, so let me start by stating a fact, which is that the tree level for gravity and amplitude in celestial basis blows up in the UV. So here I have to be very careful because there's we can't say UV in the celestial basis, right? Because if you recall, the Marin transfer was an integral over all energies. So we're mixing IR all the way up to the UV. So yeah, here I'm just making reference to, well, what is the blowing part of the integral? So I'm just saying that the top part, the infinity, is the one that's going to explode this for gravity and amplitude. Okay. However, celestial string amplitudes, they are finite in the UV, and they're guaranteed to be so because of this exponential factor over here. So we say that that is it has a soft behavior on the UV light.
I have a question. In general, the S matrix for the massless scatter is really defined because in general it's divergent.
Yeah.
Is that IR divergent related to this or something different?
No, I think it's something different. I don't think here the aim of the celestial parameter is to provide a correct prescription of the IR behavior of the S matrix in the massless case. I don't think this is going to solve the issue.
So here you have that issue as well because
Yeah,
supposedly
yeah.
it's a chain of bases. So
Yeah, you're supposed to have it. Yeah. It would be great to know the answer of that question. Yeah. Okay, yeah, so I was saying that they're guaranteed to be finite. So it seems to me that if you want to study what's going on in the UV light sector of the celestial CFT, it seems to be that the string amplitudes are a really nice playground to at least start having some intuition. Okay, so this is just one motivation. So there's this next one, which is no more linked to the actual work that we did, which is the observation that, okay, if you start with a string amplitude and you take the alpha prime into zero limit, you recover field theory amplitude. So now this alpha prime is just a recurrent factor that's up here in the string amplitude. So as I have where the argument to see that this is true, is to recall that this alpha prime factor is roughly 1 over the tension of the string. So essentially taking alpha prime into 0 is equivalent to taking the tension of the string to infinity and thus having a string at all, right? With only point-like particles. So yeah, this is just how we argument to see that this is actually true. There's of course a whole mathematical procedure to understand it more correctly. Okay, so this is true in the momentum basis. And as I said before, we can translate momentum basis to the celestial basis by performing a Melvin transfer. So okay, we can translate each individual corner into the celestial sector, right? So now the question arises: is there any way possible that we can go from celestial string amplitudes to celestial field theory amplitude? So that's the question that we have to answer. Okay, so the original work was done by Stiegler and Taylor in 2018. They analyzed the 4.2 level amplitude in the case of gluons and gravitons, and they found that if you take the forward scattering, or equivalent the large arc limit, where R is just a conformal ratio. So we're going to see the explicit form of this R. So if you take this limit, you will recover the celestial field theory amplitude. So now there's also the work of Donet, Grivet, Gonzalez, Puma, and Rojas, where they analyzed what's going on with the 4-point amplitude at one loop level.
A question: in the string amplitude level, the UV divergent disappears, right?
Yeah.
And so just in the limit, you get this divergent again.
Yeah. Yes. It was done by these authors over here. They analyzed what's going on at the loop level, and they found that if you take a correct model speed limit, you're going to recover what low Gabriel amplitudes. Okay, so however, the full picture is not that clear because if you take higher amplitudes, you're going to have more conformal ratios. So which one do you take into infinity? That's not that clear. And there's also the fact that was first noted by these authors over here that if you take different values of this R limit, you also recover the same prescription. So instead of taking large R, you can also take small r, so R going to 0. Yeah, and they also provide you with the correct prescription. So yeah, this it's not quite clear what's going on if you take higher amplitudes. So yeah.
But you're taking the cross ratio to infinity and also taking the tension to something?
No, just on this sector is just the cross ratio. Yeah.
And what happened to the tension
To
then?
the alpha prime? Yeah, it's just, you're gonna see it later, but it's just gonna be a factor multiplied. Yeah, of course, the naive expectation is, okay, we should still try what's going on if I take alpha prime into 0 limit, right? But we're gonna see that, this will not provide a correct limit. You're gonna see it explicitly because it's factorized in a very particular way. Okay, so hold on just a minute. All right, so we then went to answer to the more specific question of what's going on to 5-point true level amplitudes in the case of gluons. So all right, so that's what we want to do. Okay, so here's the most celestially picture that I could find. So it's just a fresco from Galleria Borghese. So yeah, we're gonna discuss the celestial string setup. So I had to have a celestial picture. Okay, so I've repeatedly said myself that you can take a Marin transform to transform momentum space to celestial basis. So here is in more specific, right? So here we have the these two terms are associated to the momentum space amplitude. And if you want to have a celestial amplitude, you perform a Marin transform, as I have it over here, for each external energy. Okay, and since we're dealing with massless particles, we can also always pick this null vector parametrization. So we're essentially writing down the for momentum in terms of some energies and some points on the sphere. So this is the bar. So these are our complex variables. So of course, we typically understand points on the sphere with two angles, right? But we can always project these angles into a complex plane. So just a stereographical projection. Okay. And this eta variable over here is just telling you the information if the particle is incoming or outgoing. So it's just plus or minus 1. Okay. So we know how to perform the Marin transform. So okay, we now then have to analyze what's going on the strings at the string sector, right? We want to have this sector over here explicitly for this 5-point string amplitude. Okay, so now essentially we will have to compute a diagram like this. So you can, if you don't have any idea of string theories, this may be quite weird, right? Because if you take an activity course, a 4-point amplitude is just some lines, right, which are described by point-like particles. So here, the difference is that we still have surfaces, so in particular the two-dimensional vertice. So yeah, we have in some sense, we have to know how to compute this. So unfortunately, we don't know how to compute this amplitude that as I have over there, as it is. However, we can research into symmetries to have more simple and calculable expressions. So particularly, I'm referring to that we can use conformal symmetry to map the left-hand side. So this is just a 4-point string amplitude labeled by some choice of momenta, so P1, P2, P3, and P4. We can map that into a sphere with 4 insertion points, presenting the exact same topology. So we have the insertions, so P1, P2, P3, and P4.
So that's for open or closed?
Yeah, open. Yeah.
So that's
open
a disk, no, not a sphere.
Sorry,
a disk?
Yes,
It's not a sphere.
Yeah, but it's one sphere.
Oh.
Yeah. So okay, we can have these sphere with the insertions. So yeah, now let me shift our attention on how do we actually compute this side, because we can actually do it. Okay. So yeah, as I said before, this is a sphere with for insertion. We can parameterize these insertions with some angles, or we can just say that we have a parameter and we call it x. So we have x1, x2, x3, and x4. And of course, naturally, since we're dealing with a quantum theory, we have to take into account every single possible insertion, right? So this translates on a picture that these points over here, they can be moving around on the disk. And mathematically, this translates to having to compute 4 integrals, right? So the amplitude will be proportional to 4 integrals of some weird functions that I don't have over here. Okay. So this is quite complicated to do as it is, because it's of course 4 integrals. However, we can again resource into symmetries. So particularly in this case, we have SL2R symmetry. So this symmetry allows us to fix 3 of the 4 insertion points. So in other words, the only one that's going to be able to be moving around is just this B1. So yeah, it is at the level of at the level of mathematics. So at the level of the integrals, this is the equivalent of just having 1 integral to compute. Okay, so now this is the story for insertion points. So 4-point amplitudes in string theory, and the story is quite similar to 5 points. So instead of having 4 integrals, instead we have 5. So we have 5 insertion points. Again, okay, this is equates having 5 integrals. We can then again resource into SL2R symmetry to reduce the level of difficulty that we have to compute. And okay, we can fix 3 of the 5 insertions. Yeah, the final product is that now the amplitude is going to be roughly double integral of these 2 parameters, x1 and x2. And some weird functions that I don't have over here. Okay, so this is just what's going on.
Just to clarify that group is because we have that's because of the one-dimensional conformal symmetry in the circle, right?
Yeah. 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 Okay. So here moving on to the specifics. So here we have the in the case of the string amplitude. So here the true level aiming to be amplitude for n equals 4 and 5 gluons in the type 1 superstring. We know that there is a really nice factorization that is true. So it's composed of a Yang-Mills amplitude and a string factor. So yeah, I think there is some generalization of this formula over here. However, for general n. However, I know that sometimes it's quite difficult to put this string factor to an integral form. So yeah, this is true for n equals 4 and 5. We're in the 5 case. Okay, so the Yang-Mills term, so this part over here is just given by the particular formula that I have over here in the endpoint case, which is done in the spin or helicity variables. So it's corresponding to these triangular numbered brackets. And we also are picking this Mandel invariance, so this Sij, which if you recall the null vector parameterization that we're using, we can put it in this very simple and compact way. So I have it over here. So in terms of omegas and some ZLG bars. Okay. So yeah, so this factorization is quite nice and we're going to use it. And okay, here we have more specifically what's going on to the string factor. Before I show you the expression, we're also using this neighboring selection for the Mandel invariance. So okay, this is the full expression. And it's true that it's quite cumbersome to see, especially at first glance. However, there's some very nice feature that I can show you. So for instance, you can see explicitly that we have a double integral. So this is the, after the SL2R fixing, we have to complete this double integral. And there's also the fact that this alpha prime is put in a very non-trivial way. So we have it at every single exponent. And we also have an overall factor of alpha prime squared. So yeah, the story that the alpha prime is not quite trivial at this level. Okay, so this is the 5-line string amplitude in momentum space. Okay, we can write it down. Perfect. So now, if we want to go to the celestial basis, we just have to compute 5 Marin transform, right? So essentially, that's what we did. So we obtain this expression over here, which is just a little bit less cumbersome than the other one that I show you. But again, I can show you some very nice properties. So the first one is that this alpha prime dependence is now really completely factorized out of the integral, and it's put in this very nice and trivial form. So we just have alpha prime to the beta. So you can see with your question, Matthias, that if you take alpha prime to 0, that's not going to provide you with the 5-point diagonal summit. So yeah, this is just a first check that you can see immediately.
So you say because it's going to go to 0? Yes.
Sorry?
Because this is going to vanish, because not equal to 0, or why?
No, yeah, it's going to vanish, so it's not going to give you the 5-point diagonal summit, and if you prefer the Marin trap. Okay, so there's also this double integral that's still present. We have some f factors. Oh, I forgot to say that this beta over here, I didn't introduce it before, is just depending on these deltas. So it's the sum of the deltas, and it's the imaginary part of it. And here we have the complement ratios. Okay, so these factors over here, so these f's and c's, they're just functions of z and z bar. And this thing over here is just also a function of z and z bar and some logarithmic combinations of x and y. Okay, so there you go. In general, we cannot perform this integral over here, at least in a closed way. Yeah, we just have to deal with these two integrals. Yeah, we cannot compute it. All right, so okay, we have the form of the celestial string amplitude. So now let's move on to the exploration of to find the value. The field theory limit. Okay, let's take a look here. So here is a set of some suitable candidates. So we have a hard scattering limit, Regge limits, collinear limits, soft limits, forward scattering limits. We can analyze each and every one. So yeah, I'm not gonna be discussing many. Why don't we didn't use the forward scattering limit, because that will take more time. However, particularly in our study, we consider the Regge limit. I mean, they have a whole history with string amplitudes. Yeah, you can take it that as a motivation. So roughly, when you're considering higher scattering amplitudes, these Regge limits, they branch out into two categories. So the first one corresponds to the single Regge limit, and the second one, multi-Regge limit. So the first one allows you to have one of the internal channels of the scattering process to be dominant over the whole process. And the multi-Regge one is allowing you to have more than one. Okay, so we analyzed the first one, so the first single Regge limit, which spoiler is going to give us the correct of your prescription. So in order to understand that, let me say just a few words. So on the single Regge limit, so just 101 basics. In order to understand the statement, we need to recall these modules of variables, so this Si, which are defined for I equals 1 to 5. And we also need this great definition for the cyclic property for the momenta in order to that formula to make sense. So, okay, we have 5 of these S, perfect. So in the single Regge limit, it's quite convenient to also define this other quantity, which is kappa. So it's defined in terms of S2, S3, and S5 in this following way. So now it's convenient to take S1, S2, S3, S4, and kappa to be the 5 independent momentum variables. So as a little note, in an endpoint scattering process, we have in general 3n minus 10 independent momentum variables. So in this case, we have 5 external points, right? So 3 times 5 is just 15, minus 10 is just 5. So yeah, from these 6 variables over here, we just have to take just 5 to be the independent ones. So of course, this is the correct choice that we can do. There's many more, but this is the one that's quite convenient. So now, in this context, the single Regge limit statement is the following. Okay, yeah. So we take S2 going to infinity, and we hold S1, S3, S4, and kappa to be fixed. So if you see the definition of kappa, it is written in terms of S5, S2, and S3. So we take S2 to infinity, and we want this quantity to be fixed. We also need S5 going to infinity at the same rate of S2. Okay, this is totally okay because S5 is no longer one of the independent momentum variables. So, okay, perfect. So this is the single radial limit statement. It has been studied from a long time ago in the momentum basis. However, it's not quite friendly in the celestial basis because it's written in terms of the minus some variables. And we, in the celestial basis, we have some z's, z bars, and some deltas. So yeah, with some process, we can translate this expression over here into the following set of kinematic collinear limits. So we take S1, 2, and to 0 is S3, 4, and S4, 5, and implicitly taking the same for the z bars. So when we perform this limit on the celestial string amplitude, we find this expression over here, which is exactly what you would get if you start from a 5-point gluon amplitude from just Jack Mills. So yeah, we say that then this set of kinematic collinear limits is providing you with the correct field theory prescription. So now, however, we also saw that this is not the most general limit that you can take. You can also just take the first one. So just take z12 into 0. And we also find this exact same expression. So yeah, we say that the field theory prescription is given by just a single set of kinematic collinear limits. Okay. So here I present you with the collinear table, as I like to say. So on the left-hand side, we have some collinear limits, and on the right-hand side, we had the x and y dependent integrand that's going inside of the celestial string amplitude. So if you recall, the celestial string amplitude was some factors of z and z bars, and we had a double integral, right, of x and y. So here's the leading order term taking the corresponding collinear limit. Okay, we just analyzed the first line. However, it would be great to understand more of the hierarchical behavior of these other collinear limits. For instance, if you take a suitable change of variables, we should recover the 4-point string amplitude, celestial string amplitude. So this is just something that we could see in the future. All right. So now let me finish with a few words. So yes, we analyzed successfully the field theory limit, where we found that taking just a set of kinematic collinear limits inspired from the single radial limit provides you with the correct field theory prescription. However, as I said before, it was not the most general one, so we just have to take the z12 into 0. So now the question remains is there any generalization of this result? So the answer is not that clear because of the increasing complexity of the string amplitudes. If you want to understand 6-point gluon amplitude, it's quite complicated. And sometimes if you go to n, this factorization property that I show you is no longer valid. But yeah, I should still say that I do think that the limit should still stay on the kinematic sector and not on the delta sector. Okay, and there's also these two other topics that we cover in the paper that I didn't have any time to tell you today. So here's just a flash summary. So we also computed the conformance of terms in the celestial basis. So it's basically factorization going on. So on the left-hand side, we have a 5-point string amplitude in the celestial basis, and on the right-hand side, we have a 4.1. So this in the case of gluons, we know that it has a really nice form. You can use the Venetian amplitude. So yeah, just put it in a very compact way. And we also discussed about the map that exists between the punctured string coordinate CFT and the punctured celestial CFT. So more concretely, we analyze this in the case of gravitons on the higher energy limit. So yeah, of course. So in the case of gravitons, for an n-point amplitude, we have in general this expression. We describe the amplitude. So we took an integral approximation, and we found out that the solid point equations are given by these scattering amplitudes, which I have over here, which they're a key equation in the catastrophe and Young, or just a CHY formulation of scattering amplitudes of massless particles. So yeah, where they naturally appear on the infrared limit. So it's weird that we're seeing these same equations appearing on the higher energy limit. Okay, so now the punchline is that a single configuration of n momenta of closed strings gets mapped into n minus 3 factorial possible vertex operator configurations given by the scattering equations. So yeah, that was the end of it. So thank you very much for your attention.
Thanks, Gabriel, for the talk.
Thank you.
So we have now time for a few questions. You guys want?
Did you compute or maybe have some intuition about the shadow transformation of
The selections on the
like doing the same analysis but with the shadow or the leaf amplitude, or for example, the Carolian amplitude? I mean, I pick those type of amplitudes because they are better behaved in comparison to the celestial amplitude.
No, I don't have any intuition right now of what's gonna if we take, for instance, the shadow transform of these amplitudes over here. I can't see anything. However, I do know that there's a paper by Sperger and Taylor that they understand what's going on these the same limit on the Carolian side. Yeah, maybe I can show you the paper later. But yeah, I wouldn't be able to tell you any intuition on what's going on in this sector. Yeah. But I can show you the paper.
Thanks for your talk. Very nice question is,
Okay.
you compute the amplitude for the planar case,
Yes.
where the chapado is trans. As I know, in the case of 4 points amplitude, the planar and the non-planar and the modules are almost equal, the amplitude.
Okay. Yeah. Is it almost equal?
Yeah,
I thought it was equal. But no.
but there is a minus,
Ah,
but are
Okay.
almost equal.
okay.
But the functional expression are the same.
Okay, yeah.
Yeah, my question is, in the 5.5 point,
What's going on?
yes,
That's a great question. I can't answer that question because I haven't done the.
because your amplitude is very different,
Yeah.
different to the 4-point case.
Yeah, to the 4 point. You said,
Yes.
Yeah. This is just because it's written in the double this interval way. So I think you can write it in terms of some special functions. So but I haven't done any calculation on compared. No, I can't. No, I'm not gonna be able to answer that question.
Okay.
I just we just work with the interval form of the string amplitude. Yeah. I wouldn't say it's quite convenient, at least on the 5-point sector. I'm going to write down in terms of these special functions. I think that's convenient in our case. That's why I haven't done the calculation.
And last question, as I know, the collinear limit.
Yeah.
It's related with the open.
Yeah, that's yeah.
Yeah.
Sir. No, go.
No, that is.
Okay, yeah.
Can you say something about?
Yeah. Unfortunately, I can't. Yeah.
Okay.
We didn't do the OP's limit of the string operations. It would be great to do it, at least in the future, because this could be related to the hierarchical behavior of this collinear table that was shown. You should be able to recover this 4-point string operative from this sector. However, if you remember the expression, the collinear table, it was very difficult to have some intuition. Yeah, it's horrible. I think you need to do some maternity change variables to recover the actual 4-point string amplitude, at least in every case except the Z12 limit, grand limit. So yeah, that's the only thing that I can say about the OPD. But yeah, that's a really nice question.
Thanks.
There's a question in the chat. There's words in this. Thanks. Question, chat.
Okay,
Zoom chat.
I'm going to.
Yes, from Matías.
Zoom.
What's about the sub-theory and string theory?
For some strange reason, I can't see the Zoom. Oh, no, yeah.
Lo voy a poner en el computador de la Jorge.
So it says, does the soft limit of the open string relate somehow to the soft limit of the closed string via open-closed duality? Yeah, so that's a really great question. In the 5-point case, I don't think so, because they're quite different to analyze, at least in the selection sector. I mean, you're more expert on that, right?
I am.
But yeah, I wouldn't say that's that they're quite related to the at least in the 5-point case. I mean, they're quite different. I guess it could say that is true. You can see that explicitly in the 4-point case. But I don't think anyone has done that calculation. I don't think so. At least in the selection sector.
At the level it seems
Yeah.
so. For me, it's not clear at the level of you. It's not like loops. I think it's more for topology. You can relate it to the tubes of closed string, perhaps. If you include loops, there is some clear.
Yeah, but that's a statement on the momentum basis, right? I don't think that is that also true on the selection basis?
I think so, but
It should be, right? But I don't think is that obvious to say that it's true.
yeah, my point is that at true level is not clear for me. But
Okay,
in
at true level is
loops,
not clear.
it could be possible.
Okay,
But
okay.
That's
Great.
all what I wanted to say.
Great. No, yeah, that's good. Okay, so yeah, you have somewhat of an answer from Anthony.
Any other question, guys? Okay, if no more questions, let's thank Gabriel again.
Great, thank you, everyone.
Thank you.
Next.
Thank you very much.
No, de ahí,